मेरा नाम धन्या और आज हम लोग स्ट्रक्चर ऑफ एटम के नेक्स्ट वीडियो में हैं, जिसमें आज हम लोग क्वांटम नंबर के बारे में सीखेंगे. Okay, students, we just finished with the Bohr model of atom or the Bohr model of atom, and Bohr had suggested that electrons are particles moving around the nucleus. So this was this was according to Bohr, but de Broglie said that the electrons are not behaves as particles and also waves. Okay, so how can the waves move around? Okay, so the big breakthrough came when a scientist called Schrödinger. Okay, Schrödinger. This particular scientist, he gave an equation of wave. Okay, and this is called as electron wave equation. And this equation helps to determine, this equation helps to determine the probability of locating an electron. So that means electron is a wave, it behaves as a wave, and the probability of finding an electron at a particular location can be found from this equation, which is called electron wave equation or Schrödinger wave equation. This equation you don't have to study, okay? So just to give an introduction to quantum numbers. Okay, so this equation of electron or the Schrödinger wave equation goes like this. It's a equation which you don't have to worry because you don't have to learn about this. So this is the equation plus d square xi. It's like differentiation, okay? So d xi dz square plus 8 pi square m square by n e minus v xi equal to 0. Okay. So here, this is an equation which you don't have to learn. It's not there in the syllabus or no need to memorize it. But in this equation, you can see x, y, and z. So these represent the 3 dimensions. So electron is a wave, behaves as a wave, and the probability of finding an electron is represented by the Schrödinger wave equation. Okay, so this electron can be anywhere in the 3 dimension, and these 3 variables x, y, and z represent the 3 dimension where you can locate an electron. Okay, now this Schrödinger wave equation gives the 3 variables x, y, and z, right? And this represents what does it represent? It represents the position or probability of finding a probability of finding electron. Okay, you cannot find an exact location, but probability of the region where it is found. Okay, just like the address, we have our district, we have the town, city, etc. So like that, it will give you the probability of finding the electron. Okay, and these 3 variables represent the 3 quantum numbers. Actually, there are 4 quantum numbers, but first we will be talking about the 3 quantum numbers. Okay, so these 3 variables represent the 3 quantum numbers. That is, what are the 3 quantum numbers? L, M, and the 3 quantum numbers are L, M, and NLM, and there is an additional quantum number S. Okay, so these gives the probability of finding the electron. Okay, now coming to the quantum numbers. So Schrodinger wave equation is not there. You don't have to memorize it, but through this Schrodinger wave equation, they suggested that the probability of the electron. Okay. So these are the three quantum numbers. So students, the quantum numbers. Okay. So quantum numbers, what does it suggest? The probability of finding electron. Okay, the correct location, exact location will not be obtained, but at least a rough idea of which region it will be found. Okay, now we have N, L, M, and S. These are the four quantum numbers, as I said. N is the principal quantum number. Okay. L is the azimuthal quantum number. M is magnetic quantum number. And S is the spin quantum number. Okay. So electrons are considered as wave, and electrons are found in orbitals. Now, what is this orbital? Spelling is wrong, sorry. Orbital. This is a very important term, orbital. Okay. Now, orbital is nothing but a three-dimensional. Orbital is a three-dimensional space where there is maximum probability of finding electron. So electron behaves as waves, and electrons are present where? Orbitals. Orbital is a three-dimensional space. We already mentioned three-dimensional. The three variables gives a three-dimensional area. Okay, so three-dimensional space where the probability of finding the electron is maximum. Okay, and also orbitals have different shape, size, and also different orientations. What are these terms? We will come to it. Don't worry. Orientation. Just be with me now. Okay. So where is the maximum probability of finding the electron? It's in the orbital. Okay. So as we move on with the different quantum numbers, we will learn about it more. Okay. So the first one is, so we will be using the term orbital frequently. Okay. So orbital is the place where you find the electron, where there's maximum probability of finding the electron. Okay. Now moving on further to the quantum numbers. Our first quantum number is the principal quantum number, which is represented by N. Okay. Now this is the principal quantum number, and this N can have positive value from N equal to 1, it can have N value 2, it can have N value 3 until N equal to infinity, positive values. Okay, but N cannot be 0. Okay, if N has a value of 1, it represents the first shell, that is the K shell. Okay, if N is equal to 2, it represents the second shell, L, M, and so on. So it is the shell. Okay. Now, it tells us about, what does this quantum number N tell? It tells us about the distance of electron from the nucleus. Yes? And also the energy of the electrons. Now, you already know that the orbitals, that is close to the nucleus, they have less energy. As they move away, the energy increases. So that is why they also tell us about the energy of the electron. So energy of the orbital is, if the electron is very close to the nucleus, they have less energy. As they move away, they have high energy. They also tell us about the energy of the electrons in different orbitals. Now, we already studied this formula, energy of the electron in the nth shell, minus 13.6 times z square by n square electron volt. We already learned about it, right? So this principal quantum number tells us about the distance of the electron from the nucleus and also the energy of the electron. Okay. So these are the n values and they represent the different shells. Okay. Now, coming to the next quantum number, which is the second one is azimuthal quantum number or angular momentum. Please remember both the names. Angular momentum quantum number. And it is represented by L. Okay. Now, here, this L tells us about the shape of the orbital. Okay. Basically, N is the shell. N represents the shell number and N represents the subshell. So shell, below the shell is, under the shell is the subshell and then the orbital where you have maximum probability of finding the electron. We'll go one by one. So we finished with shell. Now we are in the subshell now. Okay. Now L has some values. Okay. L can have values 0, 1, 2, 3. Okay. Now, if L has a value of 0, okay. If L has a value of 0, then it represents the subshell S. Okay. And this is the name of the subshell. So L represents basically the subshell. Okay. And also I said the shape of the orbital. Now the shape of S orbital is spherical. S is spherical in shape. Okay. So S orbital is spherical in shape. So this is the S orbital. So we have S orbital and also the dimensions I'm just mentioning. this is Z, this is X, and this is Y. Anyway, this is the either way you can show the dimension. This is the s orbital. So what shape does it have? Spherical shape. Okay, so if L has a value of 0, it represents the S subshell and it has spherical shape. Okay, and second one, if L has a value of 1, it represents the P subshell. Okay, and P has a dumbbell shape. It has a dumbbell shape. Dumbbell shape. Okay, so the dumbbell shape, just like this. This is the dumbbell shape. This is for P. Okay, this is for P. So if I represent it along the axis, it will be like this. This is along the y-axis. Use another color. So if I represent along the axis, this is along the y-axis. This is along the z-axis. And this is along the x-axis. So it has a dumbbell shape. Okay. Now, coming to the next one, the d orbital, or the d subshell, sorry. It has a double dumbbell shape. Dumbbell shape. F subshell. Now, F subshell has a complicated shape. It has an 8-fold structure as shown in the picture. Okay. Now, so we studied about the shell. We get the subshell. We have the shell and then we have the subshell, which is represented by the azimuthal or angular quantum number. Okay, so it's like the shell. Under the shell, we have the subshell. After that, we have the orbital, where there's maximum probability of finding the electron. Now, the value of L is from 0 to, ranges from 0 to n minus 1. Okay, for example, if I have n value, L value, okay, now if I have n value of 1, okay, so L value will be 0. So you have to find this range, see this range, okay, it will be 0. And it represents 1s. That is, it is representing the shape. It is 1s. It will have a spherical shape. Okay, it represents s. Now, there is only one orbital, so it is 1s. Okay, now if n value is 2, it will be 0 and 1. See this, 0 and 2 minus 1 is 1. So it represents this 0 represent S and 1 represent the p orbital. If you see the before chart. So it will represent S and p. So this is 2s, 2 is the principal quantum number n. So 2s and 2p. Okay. The third one will have 0, 1, 2. So just go with this formula. So it will represent, this 0 represent S, P and D. So there will be 3 orbitals S, P, D. Or 3 subshells, S subshell, P and D. It is represented by 3S, 3P and 3D. If it is fourth one, 0, 1, 2, 3. This is, now you will know, S, P, D and F. So there will be 4S, 4P, 4D and 4F. Now, here the number of subshells. This is the number, this is the subshell, right? The number of subshells in a shell is equal to the number of shell. Okay, so here, so just so here for the number of subshell, here it is, for how many subshells are there? There is one subshell. Okay, the principal quantum number is 1. Here there are 2 subshells. The principal quantum number is 2. Okay, so if there are 3 subshells, it will be 3. Okay, number of shells is 3. Here the subshells are 4, so there are 4 shells. Okay, now coming to a question. So I hope you will note down this, right? Now, coming to a question. Or coming to a formula first, which is very important. So note down as important. Now, orbital angular momentum of an electron, which is very important. Sometimes they ask, okay, is given by the formula h by 2 pi, you know, the h is the Planck's constant, root of L plus 1. Okay, coming to a question number 1. You have to find the orbital angular momentum of electron in 3p subshell maybe. Okay, so you have to find the values, the n value. If the n value is 3, what will be the p value? Sorry, n value is 3. You have p. The L value for P, when it is P subshell, the L value will be what? 1. You know that, right? So if you know the L value, you can substitute in the formula, right? So h by 2 pi, root of 1 plus 1. So when you solve it, you will get the answer. So if you know the S subshell, what is the L value? If you have the P subshell, what is the L value? All these you must know in order to solve these questions. Okay. Now students, moving on further. The third quantum number. I hope till here it is clear. So we have the shell, which is represented by the principal quantum number. Then we have the subshell represented by the second quantum number, which is the azimuthal or the angular momentum quantum number. Okay, so the third one is the magnetic quantum number, which is represented by M. Okay, so N represents the shell number. M represents the, L. L represents the subshell. And the M represents the orientation or It also represents the number of orbital. It tells us a lot of things about the orbital. It tells us about the number of orbitals and the orientation. Okay, now m value ranges from minus L to plus L. Okay, so m value represents the different orientations of the electron cloud in a particular subshell. So it represents the orientation of the electron cloud in the different subshell. It also represents the number of orbitals. Okay, and the value of m ranges from minus L to plus L. Let's check out how. Okay, so first is the shell number. Under it is the subshell. Under is this the number of orbital. Okay, now please remember this range. Okay, now I have L. Okay, if the L value is 0, so definitely it will be S subshell. What are the value of m? So minus L to plus L. So m will have a value of 0. And how many numbers are there? It is representing one orbital. Okay. If L value is 1, it is represented by P. Okay. And it will have value 0 and 1. Okay. So okay, how many orbitals are there? 2 orbitals are there. So it tells you about the number of orbitals. Okay. Okay. If it is P, okay, if the L value is 1, okay, see the range, minus L to plus L. So it will be minus 1, 0, plus 1. So how many orbitals are there? 3 orbitals are there. Okay. Then if the L value is 2, then it represents the d orbital. So minus L to plus L. So minus 2, minus 1, 0, plus 1, plus 2. How many are there? 5. 5 orbitals. And if the value is 3, then it represents F. It ranges from minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. And how many orbitals are there? 7 orbitals are there. Now, students, representing the different orbitals, okay, or here, in case of S, how many orbitals are there? 1, right? So I just make one box here. Okay, here how many orbitals are there? 3 of them. The shape is not like this, so just this is how it is represented in the textbooks, okay? So here, these are the 3 orbitals I'm drawing, okay? These orbitals will have the electrons. The third one, next one, 5. 1, 2, 3, 4, 5. Right. The next one is 7. 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, 7. Okay, so these are the subshells. Okay, and these are the subshells, and or these are the orbitals rather. These are the orbitals. These are the subshells, SPDF, and these are the orbitals where there is maximum probability of finding the electron. Okay, here. Let's take an let's do it with an example. Okay, so n value, L value, M value orbital. Okay, if n value is 1, L is 0. It represents what? The S subshell. And M value is also 0. And we have 1s orbital. Right? When n value is 2, we have 0 and 1. I'll write the 1 below. Okay. 0 and 1. 0 represents the S, 1 represents the P. And this will be 0. This will be minus 1, 0, 1, plus 1. This will be 2s. 0 represents the s orbital, right? This is 2p. 3 orbitals, 1, 2, and 3. Now, if n value is 3, we have 0, 1, 2. 0 is represented by S subshell. This one is P. This is D. So this is 0. This represents the 3S. This is minus 1, 0, and 1. It represents the 3p orbital. This one is minus 2. 2 represents the D. Minus 2, minus 1, 0, plus 1, plus 2. How many you have to draw? 1, 2, 3, 4, 5, 6, and 7. This represents the 3D. Similarly, you can draw for the fourth one also. Right? You can represent for the 4s, 4p, 4d, and 4f orbitals. So students, this is how shells, n represents the shells, then you have the subshells, which is represented by the L, and you have the orbitals represented by M. It tells you about the number of orbitals, and also it tells you about the different orientations of the electron cloud. Okay, and I already told you about the M values. Okay, now coming to a question. How many subshells and orbitals are present in n is equal to 3. So the principal quantum number is 3. So when n equal to 3, we have L. L value is from 0, 1, 2. So M value, when M value is 0, L value is 0, M value is 0. Yes. When L value is 1, it will have 0, minus 1, 0, and plus 1. 3 of them here. When L value is 2, it ranges from minus 2, minus 1, 0, 1, and 2. So, how many are there? Here 1, here 3, here 5. So, Total how much? 1 plus 3 plus 5. How many subshells are there? How many orbitals are there? 9. Right? So, number of subshells is how much? These are the subshells, S, P, and D. There are 3 subshells, right? But how many orbitals are there? 9 here. Here there is 1, here there is 3, here there is 5. That makes 9, right? So, the same thing we can determine, instead of doing this lengthy way, we can also determine by the formula, number of orbitals is given by the formula 2n square. Okay, so we have so students, if they ask you for the number of orbitals in a shell, it is given by the formula n square, just in competitive exams and all, if you have to save time, you can use this formula instead of doing this lengthy way. Okay, so this I just explained it. So n square, number of orbitals is given by n square. What is n over here? Our n is 3. So 3 square gives you the same answer. Okay. And another formula which I want to refer to is these are just shortcut formulas. So number of orbitals in a shell is given by n square. Okay, this is one important formula. Number of orbitals in a subshell is given by the formula 2l plus 1. Okay, these two formulas, please remember. Okay. For example, if I have a question like this. Find the number of orbitals in n is equal to 2. Okay, number of orbitals in the shell. Okay, this represents the shell. So it is given by n square. So 2 square will give you 4. Okay. So please remember these two formulas. Now students, the next one is the quantum number, spin quantum number. Okay. The spin quantum number, fourth one is spin quantum number, which is represented by S. And this tells you about the spinning of electrons. This tells you about the spinning of electrons about its axis. And it has two values, plus half and minus half. Sorry. Plus half and minus half. So these are the two values of the spin quantum number. Maybe one is representing the clockwise, the other one is anti-clockwise, maybe. Okay. So for example, if I have to represent, suppose this is the orbital. Okay. So suppose if I have electron with maybe plus half like this, the other one will have minus half spin. So I represent it like this. So this is how you represent the electrons, which we will further study. Okay. So that means if I have the third electron, it cannot come in the same. I cannot draw it in the same orbital. It has to go to the next orbital. Okay, so some of the conclusions that came out here was that one orbital, this one box, can accommodate only 2 electrons, like one with spin positive half, one with spin negative half. Okay? For example, if I have a question, find the number of electron in second shell. Okay, so I have n is equal to 2. So what does it give you? 2n square, that is 8. 8 electrons you have. Okay, over here we will draw it and find out n, l, m. If n is equal to 2, L will have value 0 and 1. M will have 0. This is -1, 0, +1. So 0 represents the S. And this one is the P. P has 3 orbitals. 1, 2, 3. Now, here, each box or each orbital can accommodate how many electrons? 2 electrons. So I'm drawing one with spin plus half, one with spin minus half. Here also, one with spin plus half, minus half, plus half, minus half, plus half, minus half. So total, how many electrons are there? Here, 2 electrons are there. Here, 1, 2, 3, 4, 5, 6. So total, how many electrons? 8 electrons. So we can we find out with the shortcut method also and this method also. Okay, so in the same question, if I ask you, you have to tell me the number of electrons with the spin minus half. So if you have to, so in the same question, you know the number of electrons, how many are there. So if you have to find out the number of electron with spin minus half. Okay, so in this particular orbit, how many electrons will have spin minus half? 1 electron will have spin, because one will have a positive half, other will have a negative half. Here in this, each orbital, there are 3 orbitals there. One will have plus half and the other will have minus half. In this orbital, one will have plus half, one will have minus half. In this also, plus half and minus half. So total, how many of them will have minus half? 1, 2, 3, 4. 4 of them. 4 is the answer. Or the other way around. If I have the total of, how many total electrons are there? Total electrons are 8. 4 and 4. 4 will have a spin of plus half. 4 will have a minus half. So 4 is our answer. Okay, so these type of questions are also very common. Okay, so students, please write some important information which will help you to solve some questions. Okay. And please remember to keep those informations in your mind. Okay. For example, number of subshells in a shell is equal to number of shell. So how many subshells are there? That many shells will be there. Okay. So subshells are S, P, D, and F. Okay. The number of orbitals in a shell is given by n square. We have done this. Then number of electron in an orbital. Each orbital will have 2 electrons. Each box will have 2 electrons, right? So that's what they're saying. We saw this also. We have solved some questions. Now, okay, so these are some important things that you need to keep in your mind. Okay, now coming to the next topic, which is our very important topic, which is called Pauli's exclusion principle, which is very important. Okay. Pauli's exclusion. You need to remember the statement for this principle. Okay. Pauli's exclusion principle. Now, this states that no two electrons can in an atom can have same value for all the 4 quantum number. Okay. So this is a very important principle that was stated that helps us to in filling up of the electrons in different subshell. Or rather, this helps us to know how the electrons, orientations of different electrons. For example, the statement is very important. You need to remember it. Okay. Sometimes they ask us a multiple choice question in the competitive exams. Okay. So which is the correct statement for Pauli's exclusion principle. So that is one of the question. That's why statement is very important. Now, students, suppose I take an example of maybe 4s. Okay. So I have each orbital will have 2 electrons. We already saw it, right? Now, here there are 2 electrons, right? One will have a positive spin, the other one will have a negative spin. So n is equal to, so for the 2 electrons, n is equal to 4 here also n is equal to 4. Okay. N is equal to 4. L value is 0 because it is the s orbital. Here also s value is 0. M value is 0 because it's the s orbital. S subshell, sorry. Okay. Now, you would be thinking all are same. But we have still one more quantum number, s. One will have a positive spin, other will have a negative spin. Okay, so there will be one difference, at least one difference. So no 2 electrons in an atom will have the same value for all the 4 quantum numbers. Okay, so this is Pauli's exclusion principle. Okay. Okay, students. Now, these are the shapes of different orbitals that we just studied. As you can see, the first one, s orbital, it has a spherical shape. Yes. P orbital has a dumbbell shape. D has a double dumbbell shape. Okay. And F is more complicated structure. Okay. So this is the S, which has a spherical shape. Now P orbital. Now you can see the 3 dimensions, X, Y, and Z. This is the 2px orbital. This is the 2py and 2pz. Okay. So these are the 3 shapes of the 3p orbitals along the x-axis, y-axis, and z-axis. Okay. Then we have the d orbital, which has a double shape and it is more complicated. So as we learned that there are 5 d subshells, right? So this is dxy, dyz, dzx, okay, and dx square minus y square and dz square. Okay, so just remember the shape, keep in mind the shapes, okay. So this has a more complicated shape, okay, and it is double dumbbell shape. And another subshell is F. There are 7 orbitals for the F subshell, okay, and it has an even more complicated shape, as you can see along the axis. Okay, so these were the shapes. So you have to know the names of the shape, okay, especially the S, P, and D. Okay, so these orbitals accommodate the electrons, right? Now, students, coming to a rule or coming to a principle which is called as Aufbau principle. Okay, so the next topic that we are going to learn is the Aufbau principle. Okay, and Aufbau, the name Aufbau has a meaning, okay, and this is called as building up. The meaning is building up rule. So building up, the meaning is building up, and this is called as building up rule. Okay, so this is not a name of a scientist. So the meaning of Aufbau is building up rule. Okay, so in case if a question is asked, which of the principles is not based on any scientist name, so you can name this Aufbau principle. Okay, so this Aufbau principle tells us the method of filling of electrons, or how the electrons are filled in different subshells or different orbitals. Electrons can just not go anywhere into any orbital as it wishes. It follows a certain rule, okay, and that depends upon the energy of the orbital or the energy of the subshell. And also, the electron always tries to be in the lowest energy state. Okay, so the electron will occupy, the electron will always occupy lowest energy level, energy orbitals first. Okay, so that's the rule. So, Aufbau principle states that the filling of electrons, or electrons are added according to this principle. Electrons are added to various orbitals in increasing order of their energies. In increasing order of their energies. So whichever orbital has lower energy will be filled first, and then later on the high energy orbitals will be filled progressively. Okay, so just taking an example. So electrons occupy the lowest energy orbital, and then they move to the higher energy orbitals. So the electrons are first filling the lower energy orbitals, and then they fill up the progressively to higher energy orbitals. Now, suppose if I have 2 orbitals, 2s and 3p. How do I know which of them has a lower energy or which has a higher energy? Okay, for this there is a rule which is called as N plus L rule. You know what is the N? N is the principal quantum number, L is the azimuthal quantum number. And you know the values of L when it is S subshell, the value of L is 0. When it is P, it is 1. When it is D, the value of L is 2. When it is F, the value of L is 3. Okay, this is the principal quantum number N. Okay, so if we use this N plus N rule for N is, in this case, N is 2 plus, this is S orbital. So S is 0 for S. So it is 2. In this case, N is 3 plus, what is the L value when it is the P orbital? It is 1. So it is 4. So clearly 3p has higher energy than 2s. So definitely who will be filled first? 2s will be filled first and then later 3p will be filled. Okay. So it is difficult to use this rule every time because it takes time, right? So there is a shortcut rule or in the books that's available to a trick to find out the filling of electron or the order of filling of electron. It's there in the textbook. So you are writing it in the order like this: 1s, then 2s, 2p. Okay. Third one has 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5d, 5p, 5d, 5f, 6s, and so on. Okay. Now, first, the electrons fill the 1s orbital because it has less energy. Then it fills the second 2s. So 1s is filled first, then 2s, then after that 2p, and then 3s. Okay. Then 2p, 4s. 3p, 4s. Then again 3d, after 3d, 4p, 5s, and so on. So this is a shortcut way to know the filling up of the electron, or easier way to know how the electrons are filled in different orbitals. Okay. So based on this, if we practice one or two examples, for example, if I take helium. Helium, the atomic number is 2. Okay, Z is 2. So there are 2 electrons. Okay, and you know every subshell, the maximum capacity of each subshell is 2. Okay, so 1s will have 2 electrons, 2s will have 2 electrons, 2p will have 2 electrons, 3s will have 2 electrons. This is a maximum capacity. Right. Now, in case of helium, there are 2 electrons. So, if there are 2 electrons, where will let's start with hydrogen first. Hydrogen having the atomic number 1. Atomic number is 1. Okay. So there is only 1 electron. So obviously, where will it go? It will go in 1s subshell, and I'm representing the electron like this. Suppose if helium has 2, the atomic number is 2. So if there are 2 electrons, so it will obviously occupy the lowest energy subshell, 1s. And what is the maximum capacity of 1s or s orbital? That's 2. Right. If I say lithium is 3. Right. So that means there are, how many electrons are there? 3 electrons are there. Out of the 3, what is the capacity of 1s? 1s, 2 electrons will come in 1s. And where will the rest of the electron? Rest means there's only 1 electron left. That will go to the 2s. Okay, then next is beryllium. Same way. Beryllium, the number of electron is 4. So out of the 4, 2 of them will go to 1s. 2 remaining. Where will it go? 2s2. Next is boron. Boron, the atomic number is 5. So out of the 5 electrons, 2 of them will go to 1s subshell. 2 will go to 2s. And 4 we have used, 1 more remaining. It will go to the next subshell 2p1. Okay. Then carbon. Carbon is 6. So out of 6, 2 will go to the 1s shell, 2 will go to the 2s shell, remaining is 2 that will go to the p subshell. Okay. Now students, here I'm just rubbing this part. Okay. Now, over here, suppose if I look at carbon, okay. Now, for carbon, I have the configuration 1s2, 2s2, 2p2. Now, you know P has 3 orbitals, 1, 2, and 3 orbitals. This is px, py, and pz along the 3 axes as I showed you. Okay. So, the electrons will occupy the x orbital, y orbital. This will not have any electron. Okay, so I'll compare it with the next one, which is nitrogen. That is the next element, which is the atomic number is 7. So I'm writing it here. So the configuration is 1s2, 2s2, 2p3. Now, how will be the configuration of the p orbital? I'm talking about the p orbital. Okay, so px, py, pz. Okay, so there will be 1 electron in px, 1 electron in py, and 1 electron in pz. It's not that, for example, in carbon, it will not, first it will try to fill 1 electron in each of the orbitals, and then they will start to pair up. Okay, for example, in px and py, there are single electron. It will remain like this. Okay, this py orbital, the electron in py will not come to px. It will remain like this. Similarly, nitrogen, it will remain as single electron in each of the orbital. Okay, now you will see the difference when I show you the next one. For example, of course, when they get excited, when they get energies, etc., they can pair up. But for now, they are like this. Okay, so the next one is oxygen. Okay, oxygen is 8. Okay, so 1s2, 2s2, 2p4. Okay, so I'm talking about the p orbital again. So px, py, and pz. Okay, 4 electrons are there. 1, 2, 3. Now they will start to pair up with this, pair up. Okay, so first they try to fill in 1 each in each of these orbital, and then if there are more electrons, then only they start to pair up. Similarly, in case of maybe fluorine, 1s2, 2s2, 2p5. Here again, 1, 2, 3. So 1, 2, 3. First they are all single filled, and then they start to pair up. Okay, then neon. Neon is 10. Okay, 1s2, 2s2, 2p6. Okay, So 1, 2, 3, 4, 5, 6. Okay. In case of neon, if you see the p orbitals are fully filled, it's completely filled. Okay, so that is why neon, it's a noble gas and it is less reactive. It's because it is fully filled and also it is stable. Okay, similarly in case of helium also. In case of helium also, helium has 2 electrons, right? So both the electrons will go to 1s. And what is the capacity of 1s? There's only one orbital and that orbital is fully filled. So that is why helium is also stable. Neon. In neon, the p orbital. What is the capacity of p orbital? 6. And has neon achieved this full capacity? Yes. So that is why these noble gases are considered to be highly stable. Okay. So similarly, we'll look at 1 or 2 examples. Okay. For example, if I say magnesium, okay. I hope the filling is clear, right? So let's check with magnesium. Magnesium, the atomic number is 12. So 1s2, 2s2, 2p6. So this is the filling of orbitals in magnesium. Okay. Then I have just an example of potassium. Potassium is 19. Okay. So it is 1s2, 2s2, 2p6, 3s2. Just follow the Aufbau rule that we did. So just follow this. Okay. So 1s2, 2s2, 2p6, 3s2. That makes how many electrons? 12 electrons. More to go. 12 plus. So after 4s, after 3s is 3p. We have one more electron to be filled. So that will come in 4s1. Okay, one more electron to go, that will go in 4s. Okay, so this is how you fill in the electrons following the Aufbau principle. This is very important, and based on these, the questions we will practice when we do the past paper question. Okay. Okay, students, the next topic that we are going to discuss is Hund's rule of maximum multiplicity. Okay, so in this, they are talking about the pairing of electrons. Okay, they are talking about the pairing of electrons in different subshells. Okay, now about this we discussed when we were discussing about the Aufbau principle. Okay, so for example, when I was discussing about maybe nitrogen, suppose I have nitrogen. Or maybe I'll start with carbon. Carbon, the atomic number is 6, right? So the filling, we already saw the order 1s, 2s, 2p. Then comes 3s, 3p, etc. Now we have 6 electrons. It has to be filled in the different subshells. So 1s2, 2s2, 2p2. Okay, so there are 3 subshells, px, py, and pz. 3 orbitals, sorry, px, py, and pz. Okay, there are 2 electrons. Okay, both the electrons cannot come in the same orbitals. Okay, first, these orbitals try to be half filled or singly filled, and then they start to pair up. Okay, so in this case, one electron will come occupy the px, then py. Okay, you can draw the spin anyway, and then pz. If there is no electron, it will come to pz. Okay, for example, I have the next one is nitrogen. It is 7. So 1s2, 2s2, 2p3. So in this case, px, py, pz. So that's why I said we talked about this when we were discussing the Aufbau principle. So here, the electrons, all the electrons will not fill up, or the pairing will not take place. Okay, this is called pairing. Pairing means 2 electrons in same orbital. Okay, so the pairing will not take place until we have all the orbitals singly filled like this. All of them is singly filled. Okay, because electrons try to be as unpaired as possible, or electrons tries to be unpaired. Okay, and then they start pairing up. Okay, now for example, then we have the next one is oxygen. Oxygen is 8. So 1s2, 2s2. They try to be unpaired first, and then more extra electrons are there. They try to pair up. 2s2, 2p4. Okay, so here px, py, and pz. Okay, now here first they try to be singly filled. 1, 2, 3, and there is one extra electron. Then they start pairing up. Okay, and I have drawn the spins like this because spin quantum number you have already studied. One will have a positive half, next one will have a negative half. So I have to draw like this. Okay, so similarly again, oxygen. After oxygen is fluorine, that is 9. So 1s2, 2s2, 2p5. So px, py, pz. 1, 2, 3, 4, and then 5. Okay, so Hund's rule was talking about the pairing up of the orbital, or pairing up of the electrons in different orbitals. Okay, so Hund's rule was talking about the pairing up of the electrons in different orbitals. So what is the statement? Statement is also important. Sometimes they give 3 or 4 statements and ask to identify the correct statement. Okay, so the pairing of electron in the orbitals of a particular subshell does not take place until all the orbitals of a subshell are singly occupied. So they try to be alone as possible, unpaired as possible, and then if more electrons are there, then they try to pair up. Okay, so the same thing happens for d orbitals also. Okay, so here let's practice 1 or 2 elements where the filling of electrons take place for the d orbital. Okay, so that We can practice and then we can use the Hund's rule for the d orbital too. Okay. So if I have scandium, okay, the atomic number is 21. Okay. The filling goes like this: 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, we have 4s2. We have one electron left that goes to 3d1. Okay. So D has how many orbitals? 1, 2, 3, 4, 5, right? So that electron will go to the first subshell or the first orbital. Okay. Then I have vanadium. Okay. So I'm just randomly taking some example. Okay. So we can follow the same order: 2s2, 2p6, 3s2, 3p6, 4s2. You just have to follow the Aufbau principle order. Okay. We have done just a while ago. So 3d3. Here also what will happen? 1, 2, 3, 4, 5. So it will 1, 2, 3. So they try to be unpaired as possible. It will not be that one electron just they try to pair up. No, it will remain like this. Now coming to maybe manganese, 25. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So here you can see 1, 2, 3, 4, 5. So all are unpaired. Okay. Now coming to iron, 26. 1s2, 2s2, 2p6, 3s2, 3p4, 4s2, 3d5. Sorry, 6. So here 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and the sixth electron. Now the pairing will start. Okay, so these are the, this is the way how they pair up. Okay, now coming to one of the special case, okay, which is copper. Copper is Cu. The atomic number is 29. Okay. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and so students, now I'll come to two special cases, okay, which you will need it in your later lessons, okay. For example, if I say chromium and copper, okay. Chromium, the atomic number is 24, okay, and I have 1s2, 2s2, 2p6, 3s2, 3p6, and according to the rule, it should be 4s2, 3d5, okay. Now students, sorry, 3d4. This should be the case. But students, D has 5 orbitals, right? 1, 2, 3, 4, 5. So 1, 2, 3, 4. Okay. Now, students, sometimes it happens that in order to for a stable configuration, what happens is that sometimes this 3D becomes as fully unpaired, like it will have 5 electrons. It will have 5 electrons, and instead this will have 4s1, because this type of configuration is considered to be highly stable. Okay, so these are only some special cases where we will be practicing this, and we will come across several examples, and you can easily keep it in your mind. Okay, why it is this kind of configuration? Because this configuration, this half-filled configuration, this is half-filled, right? So the maximum capacity is 10, and this is half-filled configuration is considered to be highly stable. Similarly, in case of copper, the atomic number is 29. Okay, the configuration should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Now you'll be able to guess what type of configuration will be more stable. Here, if instead of 9, if I put 3d10, and here if I put 1, that means what? It is fully filled. Just like neon I discussed. Whenever the orbitals are fully filled, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These fully filled and half-filled orbitals are considered to be highly stable. Okay, so here, well, of course, they don't behave as a noble gas or anything, but then they are stable because they have fully filled orbitals. And this also, chromium is also considered to be stable because of the half-filled orbitals. So sometimes some changes like this. So these are some special cases which I discussed. Okay, students, in the next video, we will be discussing some past paper questions related to this atomic structure lesson. Okay, which is very important from the point of view of JEE. Okay, so thank you, students. That's all for today. Thank you. Have a great day.